Good evening, everyone, and welcome back for day two of regulatory analytics. So, yesterday we had introduced ourselves to the concept of regulatory compliance, and we had taken a brief look at application of AI and ML within the field of the regulations. So, today, carrying on, building on from yesterday, we'll be covering a few very important concepts that are used in AI and ML. So to begin with, we'll start off with CRISP MLQ. Now, CRISP MLQ is the backbone of every AI and ML project. Without CRISP MLQ, most of these projects would not work. What does CRISP MLQ stand for? It stands for Cross Industry Standard Practices for Machine Learning with quality assurance. So, using CRISP MLQ, we can, build any AI and ML project. Now, a lot of times people don't follow this methodology, and that often leads to failure. So, this practice, this procedure has been defined to ensure that whatever project you're working on, that project is successfully implemented. Okay, so let's focus on that. So we have 5 things that we'll cover. We'll start off with stages of analytics. Then we'll take a look at CRISP Mlq methodology. We'll cover supervised and unsupervised learning. We'll look at error functions and underfitting plus overfitting. So first thing is stages of analytics. Now, whenever you're working on any sort of analytics related project, this is the standard procedure that you will be following. These are the basic steps that are performed by anyone who is undergoing a analytics project. Be it a project you're doing on your own, be it a project you're doing for a client. And analytics is a very important part of data science. All right, so let's see what all we have here. The first chapter is known as Descriptive Analytics. Now, what is the meaning of Descriptive Analytics? In Descriptive Analytics, we are trying to describe what has happened. All right, so we are taking a look at different use cases, right? Yesterday we had discussed a few use cases. Now let's say we are talking about oil spills. Now, oil spills are a very, very common thing. All right, they are a very common thing and they happen a lot of the time. So we have regulations in place to ensure that these spills don't happen, right? But they still do because everybody is trying to, maximize their profit. Okay. So everybody is trying to maximize their profit and they are trying to understand why these spills have happened. So it is also important for us to understand if you are a regulatory body and you're trying to implement some new regulations based off of past, past issues. So this is the first step you would do. You would take the historical data and you would try to describe what happened. Now let's take a use case. The use case is something that we will that is known as deep water horizon oil spill. So deep water horizon was a oil was a it was an oil spill that happened in Gulf of Mexico. The Gulf of Mexico is a small water body that is, as the name suggests, it's near Mexico and Texas. Okay, so Gulf of Mexico, there was a oil platform called Deepwater Horizon owned by BP. Okay, and there was some fault in that platform, and it started leaking. Now this is considered the largest oil spill in human history, and this happened about 12 years ago. All right, so if you're trying to analyze this use case, the step one would be, why did it happen? Now there were some faulty pipes. Okay, so if you're trying to understand why did it happen, we go with diagnostic analysis. Okay, we go with diagnostic analysis. So in diagnostic analysis, we are trying to figure out why something happened and how did it happen. So here, it happened because of faulty pipelines. So faulty pipelines were there. So they were trying to, save their cost. All right. And they had an inadequate safety system. And because of this, the pipeline burst and there was a fire and it started also leaking. Okay. So here you can see that again, these corporates, they are trying to cut their cost. So you have faulty pipes due to cost cutting methods being implemented. Okay. Then we come into predictive analytics. What will happen? So here we'll try to predict what will happen. Now, what will happen if there is an oil spill? Obviously, we are talking about damage to the sea life, the plants, the animals, the microbial creatures. They would all suffer massively because that is not their natural habitat. That is a pollutant for them, right? So that is step 3, where we are trying to predict what would be the implementation of this, what would be the final outcome of this. And then we have prescriptive analytics, where what should be done. So what should be done here? In this case, this organization was fined nearly $4.5 billion. And overall, with the charges, penalties, etc., their total cost came out to be nearly $65 billion was how much they paid. So this is where prescriptive analytics comes into the picture. Now, if you're working on this use case, you would obviously recommend heavy fines to those who are responsible for this. Similarly, you will also be recommending new regulations. All these things would fall under step 4. So these are the 4 steps that we follow in prescriptive. These are the 4 stages of analytics. All right. So then moving forward, we have the CRISP Mlq methodology. Now, crisp Mlq methodology, as we had discussed, is the bedrock of any AI and ML project. Now, this contains 7 steps. These 7 steps we use to build, deploy, and keep an eye out for any project that we are working on. Okay, so here we start off with business understanding. Now, what is business understanding? This is our understanding of the business requirements. What all do we need for this business? Okay, do we need anything special? Do we need anything unique? What is the objective? What is the client's requirement? All these things we cover in our business understanding. Okay, what are the limitations of clients? Like let's say, for example, you are working for a client who's trying to come up with some new financial regulations. Now, obviously, you would say that we can put a control on this, we can put a control on that. But at the same time, they would say that these specific sectors should not be impacted. We are not trying to stop people from doing business. We are just trying to make them do business on an ethical scale. So that would be a constraint. Then we have data understanding. In data understanding, we try to understand our data. What sort of data do we have? Okay, is it, for example, tabular data? Or is it time related? Or as we know, is time series data? Do we have, quantitative? Is it qualitative? So there are so many things within data types, within the data, that we have to understand. Where are we getting the data from? Are we getting data from some RDBMS sources, like SQL related sources? Is it from some NoSQL source like MongoDB? Is it from some, other web sources in the form of HTML or XML or JSON format? So we have a lot of different data types. All right, we have a lot of different data sources. So understanding this and understanding the business is the key. Without understanding this, we cannot really, do anything. Okay. So first we try to understand what is the business requirements, what are the business constraints, and then we try to understand what sort of data is available to us and where are we getting that data from. Okay. Then we go to step 2. Step 2 is data preparation or data engineering. This can also be known as pre-processing, EDA, and feature engineering. So pre-processing deals with the cleaning up of data. So whatever data we have, we try to clean it up. Okay. Whatever problems are there, for example, if you have missing values, how do you deal with these missing values? If you have duplicated values, or if the data type is wrong, all these things we try to deal with. Okay. Then we come to EDA. EDA is also known as exploratory data analysis. Okay. In EDA, we do the visualization. We try to visualize our data. Okay. And then finally, we have feature engineering, where we try to select the best features, your features that will give you the best possible output. That selection is done in feature engineering. So this is step 2. So far, we have only worked with data. We have not done any model building yet. That will come in step 3. So we come into model building. In model building, we are trying to find the best possible model. Which model to go for? What is the best model that is available to us? And we have so many different kinds of model available that this step becomes very, very important. Trying to pick the ideal model is very, very important. Here we check for the accuracy, or we can check for the error. So we can check for either of these things. And we are trying to make sure that our accuracy and our error are both high. Sorry, accuracy is supposed to be high and error is supposed to be low. So we are trying to build the ideal model. Now, if you're facing a scenario where your accuracy is low or your error is high, we can do 2 things. We can either go back to step 2 and perform feature engineering, pre-processing, etc. again, or we can go to something called as hyperparameter tuning. Now, whenever you're building a model, there will be some sort of hyperparameters that are affecting how your model is built. What are these hyperparameters? That is something that we'll cover as we go along these courses. But using this hyperparameters, we can build our own model. Okay, we can make changes to how the model is being built. So this can improve your performance. This can improve your model performance. Okay, so that is why we go with hyperparameter tuning. Once that is done, we go with model evaluation, where we are taking the testing data and we try to check for the accuracy here. If your testing data is good, then you move on to the next step. If your testing accuracy is poor, then you go back to the model building stage. Okay. Here we are dealing with unseen data, data that the algorithm has never seen before. Okay. So here we are getting a different sort of model evaluation. All right, here we are evaluating different kinds of data. We are trying to see what is the best possible option for us. And then finally we come to deployment. Deployment is where you are deploying your model on some sort of UI. Now, deployment is a very important part. Why? Because let's say you're working for a governmental organization or any sort of NGO or a law firm, right? Now these organizations will not have, probably they will not have technical people. That's why they are outsourcing your work to you as a data scientist. They are not having these technical people. So we cannot give them the raw model as is. We cannot give them the raw data, the raw output as is. They will not be able to use it anywhere. Okay, they will not be able to use it anywhere. So this is where our deployment comes into the picture. You're deploying the model on some UI that the end user can easily navigate. Okay, so this is where our deployment comes into the picture. Right? Once you deploy the model, that is not the end of the story. It's just going to be the next part of the story. The next part is monitoring, where you're looking at your model performance. You're trying to make sure that you're keeping a constant eye on your model performance. How is it behaving? Is it able to work properly or not? If it is not working properly, why is it not working properly? How is it behaving with unseen data? All these things we keep an eye on. And then finally, we have maintenance. Maintenance basically is model upkeep. You have to make sure that your system doesn't crash, your model doesn't crash. If you have any sort of problems within the model, you have to make sure that it doesn't break down. So this is where our CRISP Mlq methodology stands at the moment. Obviously, these project methodologies are constantly getting redefined, upgraded, new features get added, all these things. So this is something that we should always keep our eye out on. Okay, so this is CRISP Mlq. The next thing we have is supervised and unsupervised data. So unsupervised data. Now, in unsupervised data, the key point is our Y is unknown. Now, what is Y here? Y stands for the output. That means the data you're working with, you don't know what the final output of that data is going to be. You don't know how that data is going to work. Okay, you don't know what your final outcome is going to be. So here we apply something we call as unsupervised learning techniques. So in unsupervised learning techniques, we are not really coordinating with we are not really controlling how the training is happening. We are just keeping an eye on it. And we are just making sure that our model is actually getting built. Okay. So what we do here is we take our data and we apply some sort of unsupervised machine learning algorithm on it. And then from that unsupervised machine learning algorithm, we get some sort of rules and patterns. Okay. These rules and patterns are going to predict how the data will behave in the future. Okay, so this will try to see how our data is going to work in the future. What sort of movements will it have based on the existing data? It is trying to fit some pattern. Okay, then we take new data we apply this rules and patterns on it and we get a predicted outcome. So basically, we are just trying to predict the behavior of the data. So that is the unsupervised learning. All right. Now, the key point here that we have discussed so far is that in unsupervised learning, the final output that you have is not known. We only know the data as is, and we try to use the data as is to make some sensible patterns. Then we can look at these patterns and see if these patterns are actually, fitting our case or not. And based on that, we can decide what to do next. And once we have decided on the patterns, the next thing that we do is we take new data, we take these rules or these patterns, and we apply on that data. And after applying it on the data, we get some predicted outcome. This predicted outcome will be in line with the existing data. Whatever the existing data may be, this will fall in line with them. All right. So this is what we call as unsupervised learning data. Okay. Then moving forward, we have supervised learning data. Now, this data is known as supervised learning data because we are supervising every step of the data. Now, supervised learning data involves a lot more hands-on from the data scientist than it would do in unsupervised learning. So, we take the historical data. The historical data is the complete data you have. Let's say, for example, we have 10,000 samples. Okay, so we have 10,000 observations from which we are trying to build some sort of supervised learning algorithm. Now, the important point here is Y is known. That means we know the output is known. We know what the final output is. So it can be some sort of classification. It can be some sort of prediction. So we'll cover both of these points and we'll try to use them. So then we have the first step is known as training and validation step. So from this 10,000 historical data, we try to take some sort of random sample. This random sample means just you're picking out random portions of the data without any specific bias towards some data. That you are not picking up some data out of your choice. It is randomly picked up by the model. So here, let's say, for example, we have picked up 8,000 data points, 8,000 samples as a random sample. So this 8,000 can be any of those 10,000. There is no fixed value. There is no fixed position from which it is taken. It is taken randomly. Okay. After we pick the 8,000, we do further splitting of the data. We have already split the data once. So this is split one. Here, we split again. Here, let's say, for example, we are taking 2,000 up there, 6,000 up there, and 2,000 down here. So why are we doing that? So we'll cover that in a second, but this is our second split. Okay. So we take these 6,000 samples that become our training data set, and we apply some machine learning algorithm. So here we are applying some supervised machine learning algorithm. So these supervised machine learning algorithms generate a mathematical equation. They are always generating some kind of mathematical equation. Okay, that is a point that we have to keep in mind. That whenever we are working with any sort of machine learning, supervised machine learning algorithm, we are always getting a mathematical equation. We take this equation and we apply it on a validation data set. Okay, and we check for the accuracy. So we get training accuracy, error, and we check for validation, accuracy, and error. If your training accuracy is good and your error is low, but your validation accuracy is low or error is high, then we cannot use that mathematical equation. That means there is some problem with the equation. So then we go back and retrain our model. But before doing that, we use hyperparameter tuning. Using the hyperparameter tuning, we try to improve our model. And then we go back and repeat this step again up until the point where your validation accuracy is also good. Once you get very good training accuracy and validation accuracy, what you do is you take the training data plus the validation data. You combine them together and you create a combined data set. And on that combined data set, we apply a final equation. And then we take that model. This is our final model that we are choosing. Then we move on to the next step where we are using either new data or we are taking this 2000 sample that was pending. Okay, so we take the final mathematical equation and we create a prediction, and this prediction is going to give us the predicted outcome. Okay, so this is known as this is where our supervised machine learning algorithm ends. So this is how supervised machine learning algorithms work. Okay, so this is again the same data splitting step. So here first we keep training our model until using only the training model until the desired accuracy is achieved. Then we move on to the validation data set. In validation data set, again, we try to ensure that our validation is high, and we use hyperparameter tuning as a measure to check that. And then we combine our data and we train the model. This training of the model is known as combined training, and then we test it on the test data. Okay. So we'll now take a look at the error functions. The first error function is known as confusion matrix. This is used when Y is categorical. Okay. What do we mean by Y is categorical? That means Y is some sort of categorical data. That means it can either be non-numeric, or if it is numeric, it is known as count data. Okay, so this is your confusion matrix. The confusion matrix, you are checking how many actual results you are getting correct and how many of them you are getting as incorrect. So this is your confusion matrix. You have true positives here. This is your positive class And this is your negative class for the predicted values. Whatever values you have predicted are put here. And this is your positive class. And this is your negative class for the actual values. So what were the actual values? So wherever the actual positive values were meeting with the actual predicted positive values, we call it as true positive. And we add that true positive here. Wherever the actual result was negative, but your model is predicting as positive, is known as false positive. Okay. Wherever your model was actually positive, wherever your data was actually positive, but your model is predicting as negative, is known as false negative. And wherever your model was predicting negative and it was actually negative, it is known as true negative. So this is the data. This is how a confusion matrix is built. All right. So first we can check the accuracy. Accuracy is obviously the results that were actually true or actually negative, false, and they are predicted as false, or they are predicted as negative and positive. We combine them, we divide them with the total number of data we have. And then error is basically the false results, both negative and positive, which are divided by the total number of data points that we have. So this is what a confusion matrix looks like. Okay. So in confusion matrix, we have a few error functions that we try to calculate. The first one is known as true positive. This is known as the precision. Precision is trying to check out of the predicted positive values, how many of them were correctly identified. So here we are talking about the predictive positive values. So whatever your model has predicted to be positive, we are trying to see if they are actually positive or were they negative results being predicted as positive. Then we have sensitivity. This is also known as recall or true positive rate. Here we are checking for the actual positive results. How many of the actually positive values were predicted as positive? Okay, so here we are taking into account the true positive and the false negative. Then we have specificity. This is also known as the true negative rate. So here we are checking for the actual negative values, that how many of the results that were actually negative are predicted as negative. Okay, so if a negative result is predicted as positive, it is known as false positive. So here we are trying to find the difference, trying to find the actual value of how many of the negative results were actually predicted as negative. And then we have false positive rate. This is also known as alpha error or type 1 error. Here we are checking for how many false positive results did we get. Okay, here we are trying to check for how many false positive results did we get. So how do we do it? This is 1 minus true negative divided by true negative plus false positive, or 1 minus specificity. And beta or type 2 error is known as 1 minus sensitivity. So 1 minus true positive divided by true positive plus false negative. Okay. Then finally we have recall. Recall is a measure to check the balance between precision and sensitivity. The closer they are to each other, the better it is. This is 2 times precision into recall divided by precision plus recall. Okay. So this is your confusion matrix. This is used when your output data is categorical. Then we have error functions. Error function is when y is continuous, when y is a numerical data and it can be represented in decimal format. So what do we do in this? First, we can calculate as the mean error. So in mean error, we are basically taking the sum of all errors and we are dividing it by total number of observations. What are the total number of data points that we have? And we are getting the mean error. Okay. So in this scenario, here we have this table. Here we can see that the mean error is coming out to be 0. Because we have some errors in the negative direction, we have some errors in the positive direction. But that is not the case here, right? That is not the case here. Because obviously we have some sort of error. So in order to check for that, we use the mean absolute error. The mean absolute error is you're taking the absolute value of sum of all errors. So when you take absolute value of anything, the negative becomes positive. So here the mean absolute error will be 4 by 4 or 1. Okay. Then we have mean squared error, where you're taking the square of all errors and then you're taking the sum of it. Okay, we have to take the sum of all errors every time, no matter what. So mean squared error, you're taking the square of all the errors and then you're dividing it by total number of observations. Okay. And then finally we have root mean squared error. So what we do in mean squared error, let's see here. For example, we have this. This would be 10 square plus minus 10 square plus 10 square plus minus 10 square divided by 4. This would be what? 100. 400 by 4. This would be 100. So the mean squared error for this is 400. Sorry, 100 is your mean squared error. Root mean square error is basically taking the root of the mean square error. So we are taking the root of this entire thing. So mean square error in this RMSE will be 10. Okay. So these are the first 4 measures. And then we finally have mean percentage error. So here we are taking the actual minus the predicted value divided by the actual value. And again, this is all divided by the total number of observations. Okay. So this will give us some answer in percentage form. Similarly, because you might have a case of negative values and positive values, we take the absolute value of the error and we end up with mean absolute percentage error. Okay, so these are the 6 error functions you might see when y is continuous. And then we have overfitting and underfitting. Now, if your training accuracy is higher and your test accuracy is also high, this is known as good fit model. That means your model is fitting the data properly. Now here, if we look at this prediction line, we'll see that it is fitting the training data quite accurately. So this is what we call as good fit model. And here in classification as well, we can notice that it is able to classify the crosses and circles into their correct classes quite properly. Okay, even if it is not very accurate. If you have training accuracy as high and test accuracy as low, this is known as overfitting. So here you can see this is a scenario of overfit. It means it is accounting for the noise in the data as well. Whatever noise is present in the data, it is accounting for that as well. So in that scenario, it is not a very good situation to be in either. You want your model to have some sort of balance. So here we can see that it is moving up too much from the data points. And here you can see that it is bending too much. So this is also known as overfitting. This happens when there is some noise in your training data set. So in order to avoid overfitting situation, we go with hyper parameter tuning. All right. And then finally, we have underfit. Underfit is also known as when your training accuracy is lower. So this is a situation of underfit. Your model is not even able to capture the trend of the training data at all. Okay, we are not even going to the test data. We are not even focusing on the test data here. So our only and our primary focus is on the training data. So when you have a situation like this, it is known as underfit. And here we have to do feature engineering again. We go back and perform step 2 again. So in case your model has good test training accuracy, but poor test accuracy, you go and do hyperparameter tuning. But if your model has low training accuracy, you do feature engineering again. Okay. So this is model evaluation and tuning. Now, finally, we have balanced and unbalanced dataset. In balanced dataset, there is a decent split of the outputs. That means that whatever output you have, there is some sort of good split, like not an equal split, but a equivalent or equitable split. That means there are sufficient number of outputs for each class. So in a situation like this, we try to split randomly to avoid bias, to avoid getting into a situation where one of the outputs is more preferred than the other output. Then we split it into 80-20. This 20 goes towards test. This 80 go towards training and testing. And then we can do 60-20 for this remaining 80%. So, and that is the ideal split. Now the ideal split doesn't always have to be like this. You can also change it up and pick up a different kind of split if you want, depending on your data set, depending on your use case. Okay. So this is in regards to splitting. So overfitting happens when we train with a lot of data. Okay. So if your data set is too huge, then you might run into a problem of overfitting because your model starts taking into account the noise in the data or the inaccuracy. Okay, because of an excessive amount of details, it is not able to capture the data correctly. Okay, so in this scenario, we can say that having too large of a data set is also a big issue. Underfitting, it happens when it is not able to capture the trend of the data. It is not even able to capture and understand the data properly enough, and it is not able to tell what is going on the data. So this is a situation of underfitting. Okay. So with that, we come to an end for today's session. So we have covered Mlq methodology, and we have taken a brief introduction into machine learning algorithms. Tomorrow, we'll be taking a look at in-depth look at pre-processing and ED. Okay, so thank you everyone for joining.